To load FWD tests raw data, we must go to the main menu, followed by selecting the FWD slash HWD back calculation section of DAPS. Once we are in the FWD analysis section, we must go to the File menu and then select the Open Files option. And by doing so, a secondary window in which we will have to define the folder in which the raw data file or files that we wish to open are located. In this case, I have here a sample file, sample FWD test raw data file. And I will also have to define before opening the file, I'm also going to have to define the format on which the data structure of that file is defined. So at the moment, DAPS is compatible with the following options: Ashto, Abatec, Carlbro/Swaco, Dynatest, GILS, QAB, Pave Testing, TBT, and Rinsun. In this particular case, the sample file that I'm going to open is stated in the Ashto format, so I have to define the Ashto format. But if I had a raw data file that was defined in any other format, the procedure would be exactly the same. The only thing that I would have to make sure is that the format that I select before opening the file is compatible to the file's corresponding data structure. So once we open the FWD raw test data file, DAPS immediately shows its contents to us. If I go to the View menu and then select the raw data file option, DAPS switches to the view in which it shows us the contents of the raw data file that we just selected and just loaded. So basically, what we are visualizing is the data structure of an ASHTO file that states the deflections, the distances, the load, the temperatures if available, the GPS coordinates if available, that were measured and collected during this particular FWD campaign. So if I go back to the principal to the main FWD test window, I can see that in this particular area of the DAPS window, I have some basic information regarding the raw data file that I just opened, such as the date in which the tests were performed, its location, its operator, minimum and maximum distances, the number of FWD stations or locations that were performed that are contained in this information, the number of sensors that were used to collect the information. And if I come down to the lower left corner of the DAPS window, I can see that in this area I have more information regarding particular stations and particular drops that were performed in each of the stations. So, for example, I know that station number 15 was executed at a distance of 282 meters, and it has all of these distinct drops in it. So all of these drops were made in exactly the same location. So if I select any particular drop, DAPS automatically updates the numerical and graphic information that corresponds to this drop, and it will also provide me with a bit more of data concerning this particular test, namely the peak load, the time at which it was executed, the temperatures if available, and the GPS coordinates if available. So all I have to do is select any drop from the list, from this list that is available, and this information will be automatically updated. If instead of selecting a line that corresponds to a drop, I select a line that corresponds to a station, DAPS will show me this particular graphic, and the parameters that are being visualized in this particular depiction are in the x-axis applied force or load, so the drop load, and in the y-axis the deflection that was measured at the center of the load plate. So in this graphic, each circle corresponds to the D1 deflection of each drop that was performed in this particular station. And if we draw an imaginary line between the first point that corresponds to the first drop and the last point that corresponds to the last drop, we can see that this line will practically intercept all of the deflections that are being shown at the moment. And so we can conclude that the linear elastic relationship or behavior, the linear elastic behavior that this pavement structure is exhibiting has a very good correlation because the deflection that is obtained is practically proportional to the load, which is basically the principal definition of the linear elastic regime. If instead of selecting a line that corresponds to a station or that corresponds to a specific drop, if I select the line that corresponds to the FWD alignment that is being depicted in the sample file that I just opened, we are going to be able to visualize this graphic here that basically depicts uh, the, um, the normalized D1 deflection, the average normalized D1 deflection, because in this case we have more than one drop per station. So the normalized D1 deflection that is being depicted here is the average normalized D1 deflection. So the average of all the drops of every station. So each circle corresponds to a particular station, and in the x-axis we have distance, and in the y-axis we have inverted deflection because the zero is up here, so the y-axis is inverted. It is very important to note that all of these graphics and tables that are being shown to us by DAPS can be very easily copied at any moment to any other software such as spreadsheet and word processing programs. And it's very easy to do this because all we have to do is right mouse click on top of the graphic area and then purely simply paste that graphic in a spreadsheet, or the same thing with the table. All I have to do is right mouse click on top of the table, copy it, and then paste it to a spreadsheet or any other software that I wish to paste the information to. And this feature is valid to all the tables and graphics that are shown in the DAPS software. So you can do this in every module, with every graphic, with every table. It's very easy to copy the information from DAPS to auxiliary programs. Included in this window, we have the analysis of deflection parameters, such as the deflection benchmark, and in this area, the window is divided in two. So we have a numerical area and a graphic area down here. In the table up here, in this area here, each line corresponds to a particular station, and each column corresponds to a particular deflection parameter. So we have distance here, distance being stated in the second column, the D1 deflection being stated in the third column, surface condition index, base condition index, etc. So it's very easy to. It's just a question of, once again, copying the table to clipboard and pasting it to any other program that we wish. We can also visualize the surface modulus. If we select a particular line that will correspond to, to a specific station, the graphic information will change. The graphic information that is being depicted will correspond to the line that was selected before, and all of this. So all of once again, all of this information can be easily copied to a spreadsheet. And at last, we have the deflections map. That is basically a heat map that depicts all of the peak deflections that were collected during the test. So in the x-axis, we have distance, and in the y-axis, we have a longitudinal. So in the x-axis, we have longitudinal distance, the distance that corresponds to the evolution of the FWD test campaign, and in the y-axis, we have the geophone or sensor distance. So if I select a particular drop, we can see that in this case we have 9 sensors, and that sensor number 9 is located at 1.5 meters away from the center of the load plate. And if I switch back to the deflections map, we can see that the maximum distance in terms of sensor is 1.5 meters. So it coincides absolutely.